let's start with a simple little map. Ellensburg, beautiful city right up here at the top. Yakima, beautiful city down here at the bottom. And there are three ridges, right? You've driven back and forth on the freeway between here and Yakima. There are three ridges between Ellensburg and Yakima, and they are northwest-southeast trending. They're not perfectly east-west. Have you ever noticed that on a map? There's a northwest-southeast trend. That's important, coming in just a bit. Menashtash Ridge is the first one that we know and love. Umtanum Ridge and Sela Butte. Now, if you work for the Department of Transportation, that's not what they call it. If you look, this is North Umtanum and this is South Umtanum. I prefer this, all right? Menashtash Ridge, Umtanum Ridge, and Sela Butte. And Sela, the little town of Sela, is just at the mouth of the canyon that way. Some of you are from Yakima. You guys call this the Ellensburg Canyon, right? But we're not calling it that. This is the Yakima River Canyon. Okay, so let's get the Yakima River on the map. Coming down from the Cascades, coming down I-90 from Snoqualmie Pass. And then at Ellensburg, out at Reinhardt, the river decides to hang a right and just goes crazy. You know that, right? Beautiful curves to the Yakima River. All right, and that's where the Yakima River Canyon is located, cutting right across these three ridges. Okay, let's do a little Geology 101. Geology 101, we learned some basic laws in geology. We used a few of them last week. If you've got folded rock layers like we had last week, the rock layers were originally flat. Remember that one? And then they were folded later on, but they weren't created in a folded pattern. They were created horizontally. That's one law. Another law is you got a bunch of stack of flat rock layers like in the Grand Canyon. Layer at the bottom is the oldest, layer at the top is the youngest. This is simple stuff. The law of cross-cutting relations is what we use a lot in geology. The law or principle of cross-cutting relations says if something is cutting across something else, it's got to be younger. If a geologic feature cuts another geologic feature, it's got to be younger. Like I'm standing in Lind Hall, I'm having a conversation with somebody that I work with in the geology department. That's a conversation that's established. And then a physics professor comes and interrupts our conversation because they don't have much social skills. That's just a hypothetical. That's just a hypothetical. Yeah, it's being recorded. I'm in trouble. So the conversation was happening, and then the interruption. The physics professor was after we got the conversation going. So we have that in geology. You establish something, and then if you interrupt it, that's the thing that came later. Well, it looks like what? We've got our ridges, and then our Yakima River is cutting across the ridges. So at first glance, it looks like we can use the cross-cutting relations rule and say what? That the ridges were here first, and then the canyon was established. And that's what the Native Americans thought. Thousands of years of observation by local people thinking about geology and developing an oral tradition to explain the Yakima River Canyon, involving a giant beaver and a giant coyote and a major fight. Some of you know this story. I'll have a little video clip to help you in case you don't know that. And the fight starts up in the upper Kittitas County, and between these two beasts, we finally have this battle coming right through these three ridges. We're just blasting right through the three ridges. And we drain all the water from these lakes in the upper Kittitas County. In other words, the Native Americans assumed that those ridges had always been there, and that this fight established the Yakima River Canyon. I'm here tonight to tell you that we view it differently. That we view it the opposite way. That the cross-cutting relations rule is real, but this is an exception to that rule. We think in modern geology, and I hope I can convince you tonight, that the Yakima River got established first, before the ridges were there. And the ridges somehow grew on both sides of the river. Now that sounds like a Native American story. Ridges growing. But that's what we think. and we have evidence to support that, and I want to share that with you on the chalkboard first, and then we'll go to all these video clips and maps and other things. Okay? So, let's continue with that. Before I erase this, let me point out then, to get you thinking like the rest of us in geology today. Look at the pattern of this river. It's not straight. That's the obvious thing. You look at a map of the Yakima River Canyon, it just hits you over the head. Looks like ribbon candy that my grandma used to serve. That tells us something. The river was not born with those curves. Those are meanders. And when you go, I'm going to erase this now, if it's okay with you. If we go to the Midwest, if we go to the Mississippi River Valley, that's a classic place to study this. In fact, my first geology class was at the University of Wisconsin in the early 1980s. No major, no motivation, barely studied. And even at the end of that first geology class, I wasn't hooked, I must say. But I remember I had to fly out to visit some friends in California. It was my second time on an airplane. For some reason, I had to fly from Milwaukee, where I'm from, to Memphis, and then change planes and fly to San Francisco. I had just done with that geology class, barely was listening, had a couple of notes in my notebook, and I'm flying, looking out the window, glued, because I'm so excited to be on an airplane. I'm flying into Memphis, and I see what I was just taught about the Mississippi River and all of these stages of meander development. And honestly, for the first time, I got excited about geology because there was the real thing out the window that I was taught in my little chapter and a little outline before PowerPoint and everything else. So I want to draw that for you. When you go to the Mississippi today outside of Memphis, Tennessee, here's what it looks like. There is the big muddy, the big Mississippi. Everything's fine, everything's good. But when you look nearby in the floodplain of the Mississippi, you see hundreds of other little river channels that are no longer being used. And you go, that's kind of weird. There must have been a lot of rivers here long ago. No. This is the Mississippi today, but these are all the positions that the Mississippi used to hold in its past. River channels migrate. River channels move. If you're patient enough, river channels will shift. Want another analogy? Not involving the physics department? I'm already doing the math here. This is not good. This is not good. Flat tabletop. Oh, we'll use the biology department this time. Dan Beck, Central Washington University biology professor who specializes in what? Snakes, rattlesnakes. Let's take a live rattlesnake, carefully, with respect. Take the live rattlesnake, put it on this tabletop, and let's be patient. Eventually, that snake is going to slither over that entire tabletop. The belly of that snake will eventually get to every square inch of that tabletop. That's how I view rivers. If given enough time, the rivers are going to slither, just like a live snake on a tabletop. They're going to slither all over that flat piece of ground, and we're going to get this kind of a pattern. Now, let me be more specific. By studying that in rivers around the world, not just the Mississippi, we now have an idea of how rivers develop patterns of their meanders. Stage 1, 2, 3, 4, and 5. Roman numerals, I don't know why, I just felt like it. Okay? Looking down on a river, in its stage 1, in its youth, the river is pretty straight. We're talking about one channel, but we're talking about channels developing curves as they age, developing meanders as they go on in years. So here's the water coming down this relatively youthful, relatively straight channel. With me so far. Go to stage 2. Time has elapsed, and our curves are our curves are eventually more exaggerated, more cartoonish. Let me keep going, and then I'll explain why. Some of you know this, others brand new to you. Let's continue. Stage 4. Oh, yes. Oops. A little too far on that one. Okay, great. Why are these curves changing their position? Let's think about it quickly, and then I've got visuals to help. The fastest water in the channel, you've been rafting, come around a curve, the fastest water in the width of that channel is on the outside. Maintain your maximum speed, you're going around the outside. The maximum velocity means erosion, a cut bank. We're going to take material away from the outside of the curve of the channel. At the same time, we've got sluggish water hugging the inside of the curve. Sluggish water means we're going to drop stuff that the river is carrying. So we're going to have erosion on the outside of the curve and deposition on the inside of the curve. Let's go to the next curve. It's the opposite. So now we have erosion on the outside, deposition on the inside. Erosion on the outside, deposition on the inside. Why are we changing the position of these channels? We keep cutting on the outside and dropping on the inside. So we go from that to that to that to that. And you go, well, why do we get to that? Well, think about it. We've got erosion all the way around this outside, not just at the maximum curvature. So even here in stage 4, we are still eroding here, depositing there. Eroding here, depositing there. We're eventually going to break through. I'm doing a lot of punching of my hands tonight. I don't know what that means. There was no punching last week. So I'm sorry for that. I don't know. It must have been a challenging weekend or something. All right. There is a stage 5. What do you suppose it is? Rhetorical question. I'll answer it. Yeah, right. Good. Eventually, our river is going to, how can I do this? Let's do it here as well. Eventually, stage 5, the river is going to become straight again. Why? Because we're going to bust through that. We're going to bust through that. The river says, I'm not going to go all the way around anymore. I'm going to go straight, and I'm out of room, so I'm going to use this. I'm going to leave this curve, which is now a lake. Still got water in it, but it doesn't have current anymore. This is an oxbow lake, another oxbow lake. And that's what I got charged up about when I flew into Memphis. I could see oxbow lakes and then these other stages as well. That guy teaching that class in Madison, Wisconsin was right. I'd never seen him outside of that classroom. I wasn't even sure he ever went outside of the building. You know, these old guys. He was right. He'd actually been out to take a look at it. Okay, how does that help us? Does that help you change your mind if you need your mind changing about was the river here first or the ridges were here first? If it doesn't help, let me clarify. We can only do these stages, 1, 2, 3, 4, 5. We can only do them if the area is flat. We've got to have that. We can't have ridges to go through these stages. It's flat back in Mississippi. Have you been? Tennessee? It's flat. And other places around the world, we need flat land, we need a flat tabletop for the snake to squiggle. And we do have, what would you say? Our canyon, stage 4. 1, 2, 3, 4, when the area was flat. River here. Then grow the ridges. Quickly about that. So uplift, driven by plate tectonics. Some of you in this room were not taught plate tectonics when you were in college. I'm not saying anything in particular. I'm just saying that. I'm just saying it's an exciting branch of geology where you throw out the textbooks in the 1960s and early 1970s, and you write the textbooks because of this major revolution in our science called plate tectonics, which explains lots of things around the world, including something like the uplift of central Washington to explain why these ridges started to grow. We could go on and on about plate tectonics, but let's just do this. Why specifically are we starting to lift and form these ridges after the Yakima River already got established? It was a vague answer until recently. Recently, here comes a map. Recently, here comes a map that's too big. Hang on. Need to make Washington smaller. That pains me to do that. Washington smaller. Okay? Washington, Oregon, California, Idaho. Right? Good. Nevada. Got to put Nevada. About 20 years ago, when I showed up at Central, about 20 years ago, I had nothing to do with this project, but it's just coincidence. About the time I showed up, the geology department at Central became a major player in something called a geodetic array, a network of instruments that were permanently anchored into the bedrock of the Pacific Northwest. So I'm going to start putting dots on this map, not just in Washington, but all across the Pacific Northwest. Each of those dots is a GPS receiver. You've heard of GPS, Global Positioning System. You've got satellites in space that can measure the location of an instrument down to the precision of the width of a grain of rice. And you can track movement of not the instrument, but the crust that's beneath the instrument. So if there's any slight movement of the crust, you can detect it, you can measure it by having satellites fixed, basically, measure moving crust, driven by plate tectonics. We didn't have this GPS network 20 years ago. We've got it now. We have numbers. We have measurements of this movement. And what I'm about to show you helps explain why Menashtash Ridge started to grow, why all of the Northwest has experienced uplift. So if you know basic plate tectonics, here's what you might know. The North American plate is moving. The North American plate is moving to the southwest about 2 inches a year. 2 inches a year, every year to the southwest. The Pacific plate off the coast of California is moving to the northwest. Faster than that, actually. 3 inches a year. There's another plate, the Juan de Fuca plate, that's moving to the northeast. I'm not sure how fast. 3 major plates doing their own thing, have a mind of their own, but the Pacific Northwest is influenced by all 3 of those motions. These stations then showed us for the first time that there is intraplate deformation. There is movement within the North American plate, driven by these major movements. Let's cut to the chase. What did we find? These GPS stations, this is really exciting when it was first discovered. These GPS stations are all moving, and they're moving in a grand choreography. There is a clockwise rotation of the crust within the Pacific Northwest, within the North American plate. That's for sure. That's information. That's data. That's not an idea. We have measurements. Coast of Oregon moving fast to the north. Pendleton, Oregon, barely moving at all with respect to that. Movement in southwestern Washington to the northeast. Out here on the Olympic Peninsula to the northeast. And the longer the arrow, the faster the motion. I'll show you some actual diagrams in a second. What's the point? The point is that rotation does not continue through Washington. Half of Washington is not playing this clockwise rotation game. So we have Northern California, Oregon, and Southwest Washington rotating, and we're slamming a screen door right into central Washington. What was the orientation of our ridges here? Our ridges, northwest, southeast trending, are a direct result of this clockwise rotation of the interior of the Pacific Northwest, ultimately driven by the Pacific plate, the Juan de Fuca plate, and in a sense, the North American's motion. This has not always been going on. Therefore, the uplift has not always been going on. I'll give you one rough date. This all started, this clockwise rotation started roughly 10 million years ago, which means that these ridges didn't even start until 10 million years ago. I know that sounds like a long time ago, but this is geology, right? We go back billions of years according to science. So this is a relatively recent story The Yakima River got through its stages when the area was flat, start the rotation, start the development of the ridges, and the ridges are still growing. There are still small earthquakes between here and Yakima, indicating that this is still a place where we are squeezing the crust and warping the crust. Layers that were originally flat are now folded. Original horizontality changing to that. So it's not an accident that we have our ridges. Our ridges are right at this boundary between moving and non-moving crust within the state of Washington, and I got bad news. We have more and more concern now about not only folds and ridges forming, which is kind of passive, but faults. Faults mean earthquakes. And so there is renewed interest in many of these faults in the shallow crustal levels now that we realize that this rotation is going great guns. This is from 1968, and the Washington State Parks had some ideas about how to promote the Yakima River Canyon. Looks like this sign never got built with these beautiful columns. But we still have a beautiful place, and we want to continue to preserve it. There will be talk about that before we quit. So you know this scene. The Yakima River now winding its way through the first. This is Menashtash Ridge, Ellensburg off to the right. And let's jump right to the Native American legend that I alluded to early.
Just south of Ellensburg, Washington, the Yakima River Canyon is a wonderful place to study and enjoy the great outdoors. Ellensburg's main street flows directly south to Canyon Road. The old two-lane highway winds its way for miles through the canyon, finally emerging at the city of Yakima. To explain the canyon's formation, the earliest residents of the Northwest, the Chinook people, created a myth involving a fight between a giant beaver and a giant coyote to cut the canyon. For thousands of years, local Native Americans made careful observations of the Yakima River and the ridges of central Washington. As the first geologists of the area, the Chinook people had an explanation for these curious canyon cuttings across the landscape. In the early days of the world, Wishpush, the giant beaver, lived on Lake Cle Elum. Wishpush always killed all of the animals that wanted to fish there by drowning them in the lake. Coyote, the wisest and most cunning of the animals, made up his mind to kill Wishpush. One day, Coyote speared Wishpush with all of his might, and the giant beaver plunged to the bottom of Lake Cle Elum, dragging Coyote with him. Coyote fought so desperately with Wishpush that the banks of the lake were torn out, water surged through the break, and they plunged through the mountains. The water rushed madly into the broad Kittitas Valley and formed another lake. The struggle between Coyote and Wishpush continued, and they destroyed the banks of that lake, and they fought as the waters surged madly into the lower Yakima Basin, and a lake was formed at Toppenish. This continued until the fighting animals made it all the way to the Pacific Ocean.
That's the older idea, that the ridges were there a long time and the river somehow blasted holes through the ridge. We're now going to try to change our view, right? With not only the meander development I was talking to you about, but the GPS, the actual geodetic information we have for moving plates and deforming crust. Great. So most of us know that exposed in the walls of the Yakima River Canyon are lava flow layers that came out of fissures that are down here in southeastern Washington, and those lavas flooded the landscape. We were talking about these last week with the creation of the petrified wood. Here south of Ellensburg, the Yakima River Canyon is still in that basalt province, but we're pretty close to the edge. Even though we're close to the edge, we still have many lava flows. Each of them have been given names and have been studied carefully by geologists that have come before them. Here's that ginkgo petrified forest layer we were talking about last week, right on top of the vantage sediment. So yeah, you can see them, right? On the edges of these channels, we can see layers of dark rock. Those are the basalt lavas. And if we look at a geologic map, this is more of a topographic map, Ellensburg down to Sela down off the bottom, Here's our 3 ridges and some major faults that have been mapped. But if we add the geology, it's the dark brown here that are these columnar basalt lavas that have traveled a long ways to get to this spot and have not continued much further off to the west. Oh, but yes, we have Google Earth now and ways to look at this from all sorts of different sexy poses. It's great stuff, and the Yakima River Canyon is one of the most photogenic places. If you're looking to try out Google Earth, this is a great place to start. This is Beaver Tail Bend, one of the features I'd like to talk to you about tonight, but this is classic stage 4, right? We've got our river developing meanders that almost cut themselves off. And under normal circumstances, we would continue to erode there and there, there and there, there and there, until we finally whittle this little guy down to nothing and we'd be on to stage 5. That's under normal circumstances, but not with the Yakima Canyon, and I'll explain why in just a second. One more time, you get the idea. Another shot at Beaver Tail Bend. Noticing some features here that we'll be talking about on our little drive through the canyon in just a bit. This is from Tom Foster down the Tri-Cities. Tom says, hey, as the crow flies, you can fly 1 mile, or you can take the river road and go 3 miles to get to that same point. That's how much we are meandering here with the development of the Yakima River.
If the terrain is flat, and if there is enough geologic time, the channel of a river system will naturally begin shifting laterally. Why is this? What causes the river to pick up and move next door? A quick trip to a research lab helps us answer that question. Stream table modeling shows that as rivers age, they go through different stages. At birth, rivers are youthful and straight, but as they age, their meanders become more exaggerated. Why is this? A close look at one curve tells us that fast water on the outside of the curve erodes the land, while on the inside of the curve, slow-moving water deposits sediment. The net result? A continual shifting of the river's channels. Well, now we're on to something. Different stages of river development tells us about the region where the river is flowing. If the land is flat, the river is allowed to push through all 5 stages, often going through those stages again and again. Craig's Hill and other deposits like it in the Kittitas Valley build a strong case that the Yakima River went through many river stages when central Washington was flat.
Look at this beautiful thing. Almost looks like art, but it's not. We're back at the Mississippi, and we've got the active channel of the Mississippi, and just like I was talking about out the plane window, all these beautiful former channels of the Mississippi River with all stages on display. You can only do that if the area is flat. I think I've hammered that well enough now where we don't have to be too worried about it. Now let's move on to the uplift idea, which was the second part of what we established. More Google Earth, this time from back at Natchez, Mississippi. And we can see some oxbow lakes that give us an indication that stage 5 has been reached many times in the past by the Mississippi. Oh, but this is different. This is the Grand Canyon of northern Arizona. Where are the meanders? Where are the different stages? They're not there. And the river is not up at the flat land anymore. The river has decided to get aggressive and has cut more than a mile down into the earth to form the Grand Canyon. Is the river that special? Is the river that energetic? We say no. We say the river's not that special. We say it's the rock of northern Arizona that is uplifting against the river to create the canyon. And that's what we want to do as we visualize all of these canyons, not only the Yakima River Canyon, but the Grand Canyon and others. It's not that the river's that special. It's that tectonic uplift is active. It's slow. You live your whole life and you don't notice it happening. But if you've got thousands and millions of years, you've got the net result that you're looking for. Back to the Yakima River Canyon, our friend one more time, Beaver Tail Bend. Even some detail here to show the Mima mounds, if you know about those, showing up absolutely spectacularly on this LiDAR. Here's what a GPS receiver looks like. It's anchored right into the bedrock, installed by former students at Central's Geology Department. This is up on Mount Olympus on the Olympic Peninsula, but every one of those stations around the northwest I showed you with the little arrows look like this. They're big structures. There's one at Snoqualmie Pass. You zoom by every time you cross the pass. So here's a more professional way to look at what I was trying to do on the chalkboard. Red dot, GPS station. Arrow, the direction that it's moving annually. Can you see this? This is the length of an arrow. This length is for 10 millimeters a year. 1 centimeter a year is that length. So if we're longer than that length, then it's more than 10 millimeters. 10 millimeters a year, something you can measure annually. And here we are at the Yakima River Canyon, and a station right on top of Lind Hall at Central's campus, and we're barely moving at all. So I talked about that screen door slamming in. And your eye might be drawn to some of these arrows that are not behaving. That's at Mount St. Helens and Mount Rainier, where we have movement of the mountains due to magma that don't care about this rotation. Well, let's move back. Here's Washington. Now we're down to Oregon. And we can see that beautiful pattern that was previously unrecognized. I'll pull back even more for you. Washington, Oregon, look at Northern California. Again, this is not an idea. This is data now. It was an idea 25, 30 years ago. It's now solid information. These positions are coming in every half a second into Lind Hall and the processing that we have. So here's a model to try to explain this, proposed by Ray Wells quite a while ago now. Here's maybe a more effective way to do it, a slight animation done by Bob Butler at the University of Portland. It's real quick. Pay attention.
So this Juan de Fuca plate, it's moving towards us here. Sierra Nevada block pushes on the southern part of the Oregon Coast Range block, which pushes on the Washington Coast Range block. British Columbia doesn't go anywhere. Seattle gets crunched.
Seattle. He's from Portland, you know. So for whatever reason, Canada's not playing, northeastern Washington is not playing. Everybody else is playing, driven by these major plates. So that's been an exciting thing in the last 15 years to help us explain things like this. Now we look at Ellensburg and Yakima and Tri-Cities. The yellow blotches are cities. Portland, Seattle, that's getting crunched. But we're now focusing on these ridges and the radial pattern of these ridges, showing us that rotation. Just like dragging your foot on a rug on the kitchen floor. You're just folding that rug over the linoleum. That's what's happening with these thin folds in the Yakima River area. I've mentioned Bob Bentley's career before. He devoted 40 years of on-the-ground field mapping. He figured this out before GPS. He mapped all these structures. Here's Central and Yakima, and he had a sense of this as well. But the GPS has confirmed what field geologists like Bentley were able to put together. So here's a snapshot, very complicated, from the late 1980s, before we installed GPS. Bob visualizing 13 million years ago, the Yakima River already kind of here, and the hint of uplift, not quite the major uplift that we were talking about in the last 10 million years. Another local geologist that we mentioned last week, Jack Powell, is helping us visualize. Here's Interstate 82 up and over Menashtash. We're going to squeeze the basalt layers because of the forces we were just talking about and develop anticlines and synclines, folds in other words, from that compression. The majority of the uplift that I'm talking about then in the 2-minute clip, the majority of the uplift is in the crux of these ridges, these anticlines. So it's not a consistent uplift necessarily, it's more exaggerated uplift in these ridges. And it's beautifully on display if you know where to look. Here we are in the Yakima River Canyon, and we can see these rock layers are folded. They are not flat. Why are they folded? Because of the clockwise rotation, because of the squeezing. And it's not just folding in this high point called Baldy Mountain in the Umtanum anticline. There's also significant faults that have offset rock layers. So there's lots of structure there, more than most people visualize. Even geologists are surprised to see the amount of deformation or folding of the rock layers. Here's another shot of Baldy in the wintertime. So kind of faint here, but here's Bentley again showing a cross-section and showing that they're not simple folds, they're folds and faults all through the region. And here's Powell saying, here's what the land surface is like going over the three ridges to Yakima. Here's this vantage sandstone layer in blue, and that's not simple. It's been broken by these red plains that are faults. Just more complicated than you originally think, maybe. Last on that comment, here's a map of earthquakes that are plotted. The yellow circles, the bigger the yellow circle, the bigger the earthquake. And I just want you to notice that, yes, there's lots of earthquakes on the west side. Yes, there's plenty of earthquakes on the east side. And the faults that have been discovered in the last 20 years in western Washington have much of the same characteristic of the faults that are over here on our side. More and more geologists are looking into the idea that this is a fault system that extends through the Cascade volcanoes, underneath the volcanoes, in other words, and that we are maybe more active seismically than previously believed. Let's just say it that way. Okay, as promised, let's take a little drive. Perfect timing. Let's take a little drive. This is an old float map from Central in the 1980s. Let's start at the north end of the canyon and work our way south. And let's just see if you recognize some of these features. How about this? When you first get into the canyon, we're driving south now, we're just getting into the canyon. On your left are some white rocks and some dark ones. What's this? That's pillow stuff from last week, right? That's the ginkgo flow that did the petrification of the trees. Oh, my God, there's some, it's like looking for wildlife. Here's a couple of geologists right here in their orange vests. Yes, one of them is Bob Bentley. This was taken back in September when we had the real bad smoke in the air. But these guys are sturdy. They're out there breathing all that stuff. And Jack Powell as well. They're looking more carefully at that vantage sediment like we were talking about last week. It's maybe not a simple sandstone. It's maybe a package of more than a dozen individual debris flows. So that first cut is that same horizon that we were looking at last week over at Vantage. And if you look more carefully, there's actually a repeat in section, which means that those white layers that you first see on the left in the canyon are dipping like this. Here's the vantage here. It goes beneath the road, comes back up over here. So there's even a tight little syncline just in that stretch of rock right as you enter the canyon on the left. Let's leave that. I told you this was going to be quick. Let's now go down the road to a favorite place to hike for many of us. There's no signs, no permanent parking place or discover passes or anything, so it's just a word of mouth thing. If you don't know about this trail, you might want to learn about it from some of us tonight. It's a beautiful trail right up this spine that gives you beautiful views in both directions. Even in wintertime, you can scurry yourself up there. So we're looking across to the west on the other side of the river, and we notice a landslide. Are your eyes trained to look for prehistoric landslides? It's right here. There's no layering through this. This is kind of a rubbly zone. Here's some faint layering we can see of bedrock basalt, and it continues over here. But this is the kind of thing that you look for if you are a landslide geologist, which I was not originally, but through the help of some of these guys, I've been able to pick them out. So LIDAR helps us reconstruct some of these landslides and find these blocks that have fallen down. It would be wonderful to give you dates, to say exactly when this landslide happened. We're not there yet. That's one of the mysteries that I promised tonight. It would be great to get detailed dates on all of these landslides in the Yakima River Canyon. For a number of reasons, we don't have that yet. Maybe we never will. Let's continue on the outside of Beavertail Bend. Some of you know what I'm going to show now. On the outside, just the outside of Beavertail Bend, there are these incredible piles of basalt rock. And if you were in the area before 1998, none of those rocks were there. A lot of rock wasn't there before 98. Some of you remember, 4th of July weekend, 1998, there was an intense cloud burst, 2 inches of precipitation in 2 hours that pummeled the landscape here. There was no time for that water to soak in, and so it cruised over the surface and created debris flows. Lots of water, but more importantly, lots of rock being carried quickly down these channels that didn't exist before, buried the road, and created large piles of these loose rocks. They're still there if you look for them. They're not as impressive as they were in 1998 because there's been flooding since. Some of those rocks have been taken away. But we take Geology 101 students from Central. Everybody that takes 101 goes down and tries to figure out how those rocks got there. And it would be entertaining for you to hear some of those ideas. I try to be as professional as I can. Let's continue. Oh, there's a landmark, the footbridge. We've all seen that. The footbridge over the Yakima River, heading up the Creek drainage. Beautiful structure. Great. Have you noticed on a map that when you go to the footbridge, here's the Yakima River coming down, of course. Look at how arrow straight the Creek is. It doesn't have our meandering pattern. It's not an accident that it's on a northwest-southeast trend. It's influenced by our folds that are developing. So this is a younger drainage than our Yakima scene, using the logic we had earlier. So yes, here's the Creek coming in from the west, dumping into the Yakima River coming from the north. Onward. Oh, great. Let's do this. Let's bust a myth or two, okay? Let's bust a myth. Right there, I get questions occasionally on, so tell me about that place where the meteorite hit central Washington. And I'm going, oh yeah, where are we talking? I was, down the canyon. Oh yeah, just south of the footbridge? Yeah. Yeah, tell me about, I want to know when the meteorite hit. Not if it hit, but like when. Give me a year. Well, there's no evidence for that. I'm sorry. There's a beautiful amphitheater there. It's almost like a beautiful place to have a rock show instead of the Gorge Amphitheater, but there's no evidence for a meteorite impact. Oh, okay, well then tell me about the big crater, the big explosive volcano that made that as well. Well, there's no evidence for that either. We need big explosive tephra and pyroclastic debris. Don't have that either. Our interpretation is boring, and it's unsatisfying when I talk to people who want to talk about these crazy ideas that are really exciting. This is an old meander. Just like at Beavertail, about the same pattern, about the same scale. We had the channel skirting right along the slope change, and for reasons I cannot explain, maybe a little bit of landsliding, the channel has moved just a little bit. Sorry, boring. Back to this periodical back in the 1960s to look to the future with developing the canyon as a scenic byway. More coming on that before we quit. Oh, but there's beautiful columns, aren't there? Exposed not only in the Yakima River Canyon, but all through the Columbia River Basalt Field. We've got a few minutes left and we're done. Let's continue south. And another mystery. Another mystery. Does this look familiar to you? We're 2/3 the way down the canyon. There's some beautiful white stripes. More than one. This is the fat one that's beautiful. It is volcanic ash from an explosive eruption, almost certainly in the Cascades. But there are other faint lines as well. So, what's up with that? Well, if you go to the brochure by the BLM, published not that long ago, that's in plain print there. Mount Mazama erupted. You know where that is. That's a volcano that used to stand as tall as Rainier probably, present-day Crater Lake. And there was a tremendous explosion more than 6,000 years ago to send Mount Mazama volcanic ash all over the Northwest. So it's not crazy to say that it's Mazama ash. If you go to this excellent publication, have you seen this one? By retired geology teacher at Yakima Valley Community College, Newell Campbell. He created this in the mid-70s. It's a road log for many of the local areas around Yakima. Newell says, yeah, check out the Mount Mazama ash beds at the edge of the Yakima River. We're not so sure. And so when this comes up, I kind of half cringe because we don't really know. There have been some local students at Central who've done some senior projects under the tutelage of Bob Bentley and Jack Powell and some of the folks who know this area very, very well. And there are conflicting results about the age of the ashes, about the chemistry of the ashes, and we know ashes are possible. Nobody's debating that. This is a photo of Ellensburg afternoon, Sunday, May 18th. This is from Bill Meyer driving into Ellensburg, trying to get home during this incredible event with Mount St. Helens ash coming into the valley. And the next day on Craig's Hill with a quarter-inch thick section of ash. So we've got plenty of ash layers. These are much coarser and much thicker, but I'm sorry. I can't deliver this with any certainty. Still debate, but almost for sure we can feel comfortable saying not Mazama ash for the big one. Even though you see it in Bentley's paper, in some others, we've moved on from that. Great, let's continue our tour. Further south yet, another landslide. Does this look familiar to you? A little recreation pull-off and across the way, almost looks artificial. Somebody quarrying there. It's not. Jack Powell's taken photos, has looked from Google Earth. He calls this the Rosa landslide. And let's get that LiDAR to help us really see that event. Can't give you an age there either. I checked with Jack. I checked with Andy Miner, a couple others. We don't have specific dates. Love to report them, don't have it. We're almost done. We're almost to the south end of the canyon. We're now south of Rosa Dam. Oh my goodness. This whole thing is a landslide. Again, we're looking, everything bathed in light here is hummocky. It's loose. It's got a coherent look that is different than the rest of the geology. So this is one of the biggest landslides in the canyon. Look at this gorgeous image. Everything sliding down, certainly across the road, almost certainly across the river. Powell thinks that this is good evidence for a lake, a temporary lake that perhaps flooded the Yakima Canyon, maybe up into the lower part of the Kittitas Valley. No evidence for those lake beds to my knowledge, but if you've got this kind of a landslide sealing off the canyon almost certainly, you must have some sort of temporary lake to deal with. Again, the LiDAR is gorgeous from that landslide. Thank you for that. Back to Newell Campbell helping us identify each of these basalt lava flows just across the river from that big landslide. And a landmark that some of you know, the old tunnel, the Rosa Tunnel, where the canyon road used to go through in the old days. Here's Jack Powell going through. It's now, he's a professional. It's now not available to people to visit, I don't think. I'm sure I'll be corrected on that. But the view in the tunnel looking north is back up our beautiful Yakima River Canyon, including our big landslide that came down across and sealed off the canyon. There are efforts underway to do more, to make this canyon accessible even more, to purchase some land, to create a new visitor center at the entrance to the Yakima River Canyon. And that is a project that is underway, it's ongoing, and there is hope to acquire the funds to make this even more accessible, more understanding, and more a part of who we are here in Ellensburg, Washington. That's it for tonight.